Let me know when you can see the screen here.
Yep, we can see it.
Perfect. All right. So I did the introduction. So thanks again for the opportunity to walk you guys through support vector machines. I know support vector machines are really difficult to understand. So my goal is to not make you guys leave or sleep. So let's see how I do. I thought I would supplement the chapter with additional information, but given that this is such a short chapter, but still dense in a different sense, I decided to stick with what the author has presented and how he has presented and in the sequence that he has presented. So we will just go through those chapters, starting with the linear support vector machines, the two variations of those, hard margin versus the soft margin, what are the differences, and then move into the nonlinear support vector machines, and then support vector machine regression. Under the hood is the section of the chapter the author characterizes it as an optional for the beginners. But I think there is a value in going into some of those aspects, even for the beginners and those of you who are more experienced in the field. Please feel free to jump in if I am mischaracterizing anything. I have used support vector machines in the past, but nowhere near an expert. I do love support vector machines. I see the beauty in them because the previous two chapters we've done, regression and, well, training models, but mostly regression, and the classification are both probabilistic models, but support vector machines is not a probabilistic model. It's purely based on geometry, so we can really use our intuition, at least in the second and third dimensional space. But the place where it becomes more complex is once we start projecting those into the higher dimensional spaces. So I will make an attempt to like walk a little bit into under the hood. We don't necessarily go into a lot of the equations, just to build an intuition. With that, let's jump into the support vector machine. One other thing, Annie did a great job in putting those discussion slides last time. I meant to put those in, but I don't have those in here. So what I'm going to do is at the end of each of those sections, I will stop the presentation, jump back to be able to see all the slides. And so feel free to ask any questions, or if you have experience in using whatever was relevant and presented in that section, please share that. And then if you have a different perspective than what was presented by the author, please share that too. So we will do that at the end of each section. And if I forget, please remind me. So with that, let's jump into the linear support vector classification. The author begins by introducing the concept of linear separability, which is pretty easy to wrap around. It's basically the classification problem where you have two classes, let's say. Would you be able to draw a line between those classes such that they are completely separable? And that concept in itself is nothing new when support vector machines were introduced in 1990s or so. Back in 1980s, the perceptron is a classification that was pretty popular, and all it did is draw a random line through the feature space and keep rotating that line until you get the classes on two opposite sides. So the author presents three bad examples here. Purple one and the red one, and the green one obviously is not even classifying anything, but these are not random. I mean, author has generated these randomly, but conceivably there exist models that can end up creating these as classifiers, as an example, perceptron. But the objective of the support vector machines is similar to perceptron. Try to draw a separable line between the classes, but draw the widest possible street between the classes. So what happens with that is your new data performs better on classification compared to the bad examples that were shown above. And so this is often called as hard margin classification or large margin classification. But here is a little bit of terminology: margin and support vectors. Support vectors are the points that lies on the margin. So perhaps I should define margin first. Margin is the two lines, the dotted lines that you see in the figure in the bottom. And so those represents how far the closest points in the feature space are of the opposite classes. And the support vectors are the vectors that are on the margins or within the margins. For large margin classifications, you do not see any support vectors on the road, so to speak. They're always on the margin, but we will come across support vectors that are on the road in the later slides too. So with that, the author also introduces the idea that the large margin classification, the support vector machines are sensitive to scale, and presents this example that as shown in the top row here. The unscaled pretty much finds the two support vectors, but draws a very thin margin. But once the data is scaled, you have two support vectors for the purple class, and you have much wider margin too. So by scaling, you're not only drawing the widest margin, but your future points, any new data that you come across, will likely to generalize better. And so support vector machine, if you're using support vector machines, scale them. Use a Scikit-Learn standard scaler. So in addition to the sensitivity to scale, support vector, especially the large margin classification support vectors, has two other issues. One is the linear separability. Not all data is linearly separable. Well, most data is not linearly separable. And the example that author presents, he has one, the green class and the blue class there. What happens in the way the large margin classification is implemented, it will not find a solution. The program will either give you garbage, or it will perhaps not even run through. So that's one issue. And the second issue is the sensitivity of the support vector machines to the outliers. And in this example, the small green outlier has reduced the width of the road, so to speak, so small that the future points will not be able to generalize well. So the problem with having a large margin classification is if you have outliers, you are likely to get a classification or the decision function here that is not going to generalize well. And so with that, the author introduces this soft margin classification where you do allow margin violations, as in you're not trying to draw just the widest possible road between the classes, but you're also letting some violations. So you're so if the data is not fully linearly separable, you could still find a classifier. If there are outliers, you can still find a classifier. And the way this is done is for each of those violations, you penalize your objective function by capital C, a number capital C. So the more margin violations you have, the more your objective function will be penalized. And so the hyperparameter C, the C's value itself will dictate how many margin violations are allowed, so to speak. And so like use a low value of C for more violations. That means it's cheap to make violations, and high value of C where it is expensive to make violations, you will end up having fewer violations. So a quick thing here is that C is pretty commonly used in the Scikit-Learn's library, but it is, so far we have introduced alpha as part of the regularization. And so just to note that the C is inverse of alpha, and so they behave in the opposite way. Just to remember that as we go along the book, we will build a lot more intuition of what that C means. But this is just an interesting connection that back to the chapter 4. But we will also be using in the later chapters too. Another interesting point to make here is soft margin classifications were introduced by Corina Cortez in 1995, along with Vladimir Vapnik. Talking about women in data science, support vector machines, especially the idea of having margin violations, was by a woman, Corina Cortez. And another thing to note is support vector machines are patented. So if you do end up using them and making money on those, as in using for your organization, be careful in advertising it. I'm not fully aware of what portions and what parts of the algorithm is patented. So do your research in that. I know that there are cases, active cases that are going, but I don't think either Bell Labs or AT&T well, Bell Labs doesn't exist. AT&T or whoever owns the patent is going to come after you, but just something to know about it. Following or within the soft margin classification chapter, the author presents 3 different ways of performing the support vector machines, and I thought I would summarize them here. The estimators, the language that Scikit-Learn uses for these classes. There are 3 estimators: linear, SVC, SVC, and SGD classifier. A quick note that the SGD classifier has come up in chapter, I believe, 3 in the classification chapter. The author did not present what it means, but he did use the hinge loss function. So what he was using for classifying the handwritten digits at that time was a support vector machine. Anyway, so linear SVC is pretty straightforward. You do need to specify your loss to be hinge, because the estimator accepts 2 different kinds of loss functions, only 2: hinge loss and squared loss, hinged loss and squared hinge loss. The default that linear SVC uses is the squared hinge, but support vector machines, the classical version of them, always use hinge loss. So you do need to change that if you want to use support vector machines. If you use the squared hinge, it still is support vector machine, so it's not a huge deal, but we do need to know the distinction here. The issue with linear SVC is it does not calculate the support vectors for you. If you do need those support vectors, you need to calculate yourself. Especially in the previous figures, when author drew those or identified those support vectors, he did actually use the code, and he did use the 2 attributes of the estimator, the dot intercept underscore and dot coef underscore, to able to calculate that. I'm not going to go into the details of it, but I will point out to what these actually mean when we get to the last section of the chapter. Another point to remember here is linear SVC uses dual by default, which is, again, we don't need to worry about at this stage. We will get to that into the section 4. But if you have large number of instances compared to the number of features, it's better to use dual as false, which is it is better to use your primal specification of the support vector machine that performs better. Usually, for support vector machines, especially when you're projecting your input space into a very high dimensional space, using dual is equal to false makes it faster. And then the next estimator for support vector machines is SVC. The implementation of this is, we will get into that actually, but we do need to specify kernel as linear to perform linear support vector machines, and then C being the hyperparameter. One interesting thing that author has used in his code is he used C to be a float of infinity, which means that the penalty of making a margin violation is a really, really huge number. So the objective function better not make any violations. So it gives you like a very, really like hard margin classifier with no violations, margin violations at all. I thought that is interesting to point out. There are a bunch of kernels. We don't need to know what kernel means at this point, but we will get into that. The third estimator for SVMs is the SDG classifier. We have come across this before. You do need to specify loss as hinge. I'm not sure what's the default loss is for SDG, but you do need to specify loss as hinge for the support vector machines. Here, the convention is not to use C as your hyperparameter, but to use alpha. So you do need to inverse it, and M being the number of training instances here. This is very, data points that this is very slow to converge because you are estimating your parameters instance by instance. So it is useful for online learning or for huge data sets, but typically not useful if you are using a small to medium data sets. And with that, we are ready for nonlinear SVM classification. So what I'm going to do is stop here and bring my four slides in the view, and then kind of see if we have any questions or experience or perspectives to share.
So I did have a question on the using the C for lower high C for large margin versus fewer margin. In figure 5-4 in the book, the author makes the point, he says that, yeah, that there's more violations when you use C equals 1. But then he goes on to say that that model on the left is going to generalize better than having a high C. Could you explain that, please?
Yeah, I can attempt, I can give it a try, and others can pitch in too. I think in terms of the generalization, we do need to look at couple metrics, right? Whether we are looking at recall or precision or accuracy. I believe the author says this one generalizes better because it seems like the two classes are mixing pretty well here in the middle. And so I believe C using 1 creates a margin that is wide enough to catch all of them versus C is equal to 100. I believe that is the reason, but I would, typically what I would do in terms of trying to see which of the two models are generalizing better, I would look at the bias and variance on the test data. And with that, I will let others pitch in.
So I can, excuse me, I can add a comment here. So first off, we're not saying that the different value of C equals 100 versus C equals 1, that one or the other will always work better on your data. Okay, that, I mean, if that were the case, then they wouldn't even bother having that be a parameter, that you would just use the better one, right? What the author is saying here is if you look at the visualizations, and I don't know if this is really obvious, but if you look at sort of the majority of where the blue points are and where the green points are, and if you were to just by eye say, what's the best way to split these? So imagine that like the blue's kind of lower left, the green's kind of upper right. Imagine that there were some new points that were more towards the upper left and the lower right, which are just sort of blank spaces right now. If a point appeared there, how would you want to classify it best? Which do you think it would be closest to? And so I don't know that to my eye, I can really tell the difference, but what the author's saying is that the top one with the more violations and the slope that's a little bit flatter, the author thinks that that is kind of giving you a better way of defining what should be blue, what should be green when you look at the whole of the points. And in the lower one with C equals 100, what you have is you have a very small number of points defining where the separation between blue and green should be. And if one or two of those points happen to just be outliers, then they shouldn't really be determining the rule for how to draw the separation. And so they're actually tilting, causing that line to be sloped a little bit steeper, a little further upper left, a little further lower right. I don't know if that helps, but that's kind of what I think the author's trying to communicate there.
Thank you both.
All right, any more comments, questions?
If I understand correctly, I think another way of thinking about this C equals 1 versus C equals 100 thing is if you have a cost that is really, really high, then as you mentioned, that's the equivalent of having a hard margin classifier. And at that point, in the limit, your entire fit will be determined only by a very small number of points, which is the whole reason for the name of the method, right? They call them support vectors. And the more that you lower the cost, the more the locations of other points start to matter.
That makes sense. Just for curiosity, I ran this with C is equal to 0.0001. That is, there is no penalty at all, or very low penalty, and you end up having margins that pretty much cover entire, pretty much every single instance is a violation, which makes sense.
Robert's comment just made me think of something. So if you're familiar with K nearest neighbors classification, right? So you just look at your nearest neighbors and you do a majority vote based on all your neighbors. If K is very small, then if you happen to be near an outlier, that could really confuse your classification, right? But if K is large, if you said, oh, I'm going to poll my 9 nearest neighbors, then even if there's one outlier, it'll tend to get outvoted. So I think that's the difference here between high penalty and low penalty, right? So high penalty means you're looking at fewer points, and so it's like K nearest neighbors with a very low K. And so if you are only near points that are very representative of the classes, you're doing a great job. But if you happen to have an outlier, then it's going to have a very strong influence. Whereas if you set your C to be very small, then that's like K nearest neighbors using lots of neighbors, or in your case, Bhanu, right? You set it to 0.01, and basically it's all the points voting. And so you're basically drawing a line between the two centroids, the center of the blue and the center of the green, as opposed to any one individual point.
Interesting you say. Go ahead.
Like, so can we say that as a general rule, you want the model that accounts for the most points? Or is that too much to go by?
I think that you know, in this case, we can visualize it, right? In real life, you have more features, even if you only have 10. I can't visualize 10 dimensions. And so you, like Bhanu was saying, you really have to go by your metrics to see, as you, let's say you started with a simple coarse grid search, right? As you try different values of C, how does that, improve? So if your data has very few outliers, you may get away with a fairly a very high value of C. But if your data is very noisy, you probably want a lower value so that it's kind of more averaging the points that are generally near the boundary.
Got it. Thank you.
I think one of the comments that I wanted to make is that I wish the author explained more in terms of, I wish it was like a whole section dealing with the kernels and a whole section dealing with adjusting the parameters, because when you're talking about C is a parameter. So when you're deploying this model, you have about 4 basic parameters that you're going to adjust. So you're going to look at the kernels, your gamma, C, degree, and then the degrees. Now, when you're just focusing on the kernel, which the author talked about a couple different kernels, the kernel choice that you use does depend on the type of data that you have. So there's actually more than 8 different types of kernels that you would use. So if you're working on a project that's image processing, then polynomial is really great for that, which the author did talk a little bit about that. But if you're doing a polynomial model, then that's when you're going to, where it's more nonlinear data, that's when you're going to have to adjust your gamma parameter for that. If you're dealing with neural networks, then you would use like a sigmoid or a hyperbolic kernel parameter. And so it's different parameters that you have to research with this model based on your data. One of the examples that the author spent time on was showing like the linear kernel. And that's because that's like a one-dimensional kernel, and it's like one of the most basic forms. But if you're dealing with different data, whether it's text or image, then you want to research the type of kernel. And that does impact how you would adjust your parameters. And I think that that part got confusing if you didn't know that or do prior research on that, because all of a sudden you see the author just showing code and you see, well, one code has where the gamma was part of a parameter that was adjusted, then another code has like where the degree was adjusted, and that's based on the different types of data that you have. So I would just recommend that when you're deploying this model, definitely research the different kernel options that exist and then how you would have to adjust those parameters. And that will help you more with, making sure that you're not underfitting or overfitting your model.
That's a pretty good point. When I was reading the chapter, I was a little hesitant to see the lineup or the way various chapters were and the concepts were introduced. But to be fair to the author, this is a very tough classification model because kernels are pretty confusing. So I've kind of like at the end come to realize that like just stick with the way the author has presented and then see where we go. With that, I think I'm going to move on to the nonlinear support vector machines, and let's just quickly cover through here. So the author starts with a very simple example here, but saying that most data is nonlinear, which is true, and most data you cannot even visualize. So it's a fair assumption to make that the data is nonlinear. And then the solution is to be able to take a simple the input features of the data and project into higher dimensional space. And the first thing, obviously, the easiest place to start is projecting into a polynomial space. Here, the example where there's one dimension x1 is projected into x1 and x square. With that, the author introduces the concept of the polynomial kernels, and using the Scikit-Learn's Moon datasets presents a couple examples. So what I did is I kind of like did a linear SVM2 on the Moon datasets just to show how different it looks like compared to the version that the author has done using a third-degree polynomial here. And you can see that just because of the way the linear SVM works there, even with the soft margins, basically the model is not expressive enough to be able to capture the details in the model, which means that the model has a high bias. And then with the introduction of the third-degree polynomial kernel, it fits better. The bias has dropped down, so to speak. But I also wanted to show you that projecting a two-dimensional space into a 3-degree polynomial will take you a 2D to a 10D projection here based on the polynomial features Scikit-Learn library here. So with that, I'm going to go to the next section here and kind of try to summarize the two different ways of introducing the polynomial kernel. One is do it externally, like literally explicitly project your space into the polynomial features, into the polynomial higher dimensional space, use the standard scalar, and then do a linear SVC is one way to do it. Another way to do it, use the SVC and the kernel poly here and specify the degree as 3. And this is where the author introduces what's called the kernel trick, which means that you are computing not necessarily computing, but you are creating a model in a high dimensional space without actually projecting all your data sets, that is the sample, into that high dimensional space. And that sounds like voodoo magic, and I guess it is, but mathematically it is possible. And so that's why it's called a kernel trick. So with that, the author moves into an example of using polykernel trick, but also introduces another parameter R, coef0 here. So the idea is that D being the degree of the polynomial that is a hyperparameter, and coef0 here, which is R, which is often referred as R, is another hyperparameter that author uses in showing two different models here. And then C being 5, he keeps the same between the two models that he compared, but overall there are 3 hyperparameters that could be fit here, and author suggests using a grid search, coarse grid search first, and then followed by a final grid search, which makes sense. And to be able to show you what that coef does, what I did is I took x1 and x2 and projected into the 3-degree space, the 10-dimensional degree space, using an R. And so you can see that R shows up in pretty much every single term where you have a order of degree less than 3, but all the terms that have the combined degree of 3, you do not have R. So this is what the author means by coef being influenced. You can change coef and change the way the higher degree terms versus the lower degree terms influences your decision boundary here. So with that, the next section, the author introduces what's called similarity features. And I think I really, really like this. So the example that he uses, he went back to that one-dimensional input space, and he picked 2 landmarks, those were in circle here, and put the Gaussian radial basis function over them. And so basically that represents how similar your data points are with respect to your landmarks. The closer you are to that point, the similar you are, the farther you are from that point, the less similar you are to those 2. And so created x2 and x3 features, which when plotted for the whole data set, creates a linearly separable plane here. So the author asked the question, so how do you pick the landmarks? One is pick every point as a landmark, in which case you are projecting your data from its input space into a m-dimensional space, m being the number of training instances. And so, so you are basically, like Ted has mentioned earlier, this very much reminds me of the KNN. So basically every point is voting whether other point belongs to its class or not. So with that's on the similarity features. And the next section is the Gaussian. It's kind of a similarity features is both an introduction to a different way of projecting data without using the polynomial kernels, but also an introduction to the Gaussian RBF kernel, I guess. At least that's how, it seems like that's how the author has approached the similarity features section. So again, Gaussian RBF kernel, the author has tested with these 4 parameters here, and kind of mentions that it uses the kernel trick. Kernel trick uses gamma as another regularization factor, because gamma determines how tall of bell curves are you putting on each of these data points. And so that determines how much the other points are considered to be similar to your landmark. And if you put those bell curves on pretty much every single data point, they are all voting for each other's, classes. Conceptually, that's what it is. I'm not sure about how close that gets to the implementation. Okay, so with that, the author again mentions about various kernels. It's difficult to make the kernels, a decision of which kernels to pick, which is the same point that someone just made. But the interesting thing here is, for kernels, since you are calculating the distance between the points, you don't have to have numeric data. So you can have text, you can take text and create the kernel distance between those two. And then you can also have DNA sequences. And the author suggests that in terms of fitting various, in terms of your the grid search and cross validation, start with the linear kernels and kind of gradually increase it to the Gaussian RBF and others next. So with that, let's move on to the computational complexity of the support vector machines. I'm pretty sure this is a huge subject. Perhaps there are hundreds of papers through 1990s, but ultimately, the linear SVC estimator will have a time complexity of number of features times number of training, m by n. And SGT classifier has a similar time complexity, but SVC has a much larger complexity, m squared times n to m cubed by n. And that's because it's computing the kernel matrix, which we will see in the very last section. All of them requires scaling. Only SVC uses the kernel trick. SGG classifier and linear SVC do not use kernel tricks. An interesting thing here is Scikit-Learn does not have its own code to do these estimators. It relies on liblinear and libsvm libraries that were created or maintained by the National Taiwan Institute. And these were primarily written in C++ and has API that interacts with Scikit-Learn. I have not looked at the code, how Scikit-Learn taps into these libraries, but I am pretty sure you could find it online, or at least into their GitHub repository. But another point to make here is SVC is slow to train, pretty obvious from the time complexity, but it is good for small to medium-sized training sets. Author doesn't really define what small to medium here, but I'm assuming that these are, like if you have tens of thousands, that's pretty much a medium. And if you have hundreds of thousands of instances, then just don't use SVC, don't use support vector machines, would be my thinking. But with that, I am going to again kind of come out of this section here, pull up all the slides, and then see if there are any questions, experiences to share, or perspectives.
I'll hop in on this one. SVMs have always been something that everyone always talks about, and it's supposed to be this kind of magic that came out and then everyone got much more accurate predictions. But in my experience, the time complexity has been a big bottleneck. Anytime I've tried to use it on the data sets I'm working with, I either have too many features, too many rows, and it just becomes much slower than the other algorithms that are in Scikit-Learn. I've tried various things where you just kind of brute force, you just say, run everything in Scikit-Learn and see how they do. And SVMs are consistently one of the ones that kind of chokes it. So that time complexity thing is a big barrier if you have a large data set.
And Ryan, what's the threshold for the large data set that you are talking about?
It just depends on how patient you are, because I'm sure you can get it to complete, but if if you're looking at a data set that has 10,000 rows and 30 columns or something like that, it completes on linear regression and a bunch of other stuff basically instantly. And then an SVM might take minutes. And then you go to hundreds of thousands or beyond, and it's probably taking many minutes, maybe even hours. So it's not that it's impossible to do, but it's just in comparison to other algorithms, it can be much slower.
Got it.
I thought I might add that with some of the algorithms that we're going to see later in the book and that, we generally know about, so like, gradient boosting, for large data sets, you're not necessarily going to get better performance from a support vector machine. So I think where they shine actually is when you have smaller data sets and you don't want to overfit them. When you're looking for something to try to see the pattern in the data and not just overfit the examples. So I think the fact that it performance-wise works better with smaller data sets actually kind of goes hand in hand with that's probably when they're most useful too.
Does using something like a GPU help with that?
It might.
Or parallel processing?
I'm not sure how easily that algorithm parallelizes. I'm not aware of a GPU implementation.
Yeah, I suspect it could be GPUized or whatever. I just don't know if there is one easily available.
Thanks.
I think the only comment I want to make to second what Ryan and Ted said about it doesn't perform well on larger data sets. I think the model in general is more suited for high dimensional data sets instead of when you have a large data set, and it depends on the industry. I think that's something else too to consider with the models, because for SVM models, if you work in like the healthcare industry where it may be extremely hard to come by, or gene therapy, some of like the gene therapy, biostatistics type of disciplines where it's very hard to come across large data sets for your particular issue that you're researching, but you may have like hundreds and thousands of features. That's where this model performs well, and you'll find that a lot of practitioners that really love this model tend to be more in like the healthcare arena. So like to give a quick example, in the field of radiology, there's a lot of research that's done in that field, that has been done in that field, but with those data sets, you can't really go back like 5 or 10 years. When humans are involved, the data sets, it's hard to get for certain specialized areas like radiology. It's hard to get like 10, 20 years worth of historical data. So a lot of data they may have maybe last 6 months, last 2 years, but they have a lot of dimensions. So that's where these types of models, you may see more industry specific professionals prefer them based on the size of their data.
All right. Thanks, Christy. Thanks for sharing that. With that, if there are no questions, let's move on to SVM regression. So I actually have learned about SVM classification before, but I have not learned about SVM regression until I read this book, and I really, really like SVM regression. Conceptually, I'm not sure how this plays out in terms of practical implementation. And the reason is because SVM regression seems to be exactly opposite of SVM classification. So what you are trying to do, what the algorithm does is instead of trying to fit the widest possible road between the classes for SVM regression, the algorithm fits the narrowest possible road such that it captures everything, it encapsulates everything and has few off-street violations. And so instead of the violations, the margin violations being between the margins, here the margin violations fall outside the margin. And I thought that's just funny that it's kind of opposite to SVM classification. However, you do need to specify an additional hyperparameter epsilon, and which kind of determines how far vertically, that is in the axis of y, your decision boundary is from the margins. The author also presents the idea that the model is epsilon insensitive, which means that it's not sensitive to it doesn't mean that it is not sensitive to epsilon, but it just means that it is not sensitive to the training instances that fall between the margins. No matter how many training instances that fall in the margin, your decision boundary and your prediction for the new data points are determined based on the support vectors, which are outside the margins. And the implementation of SVM is using the linear SVR estimator as shown here. This is the one where epsilon is equal to 1.5. So that's the linear SVM regression. You could also do nonlinear SVM regression by using the class SVR, and the kernel poly is the example the author has presented here. The concept is pretty much similar to what we saw for SVM classification, nonlinear classification. You're again projecting your data into a high dimensional space and using a polykernel, and you are determining the decision boundary without actually projecting the data itself into the higher dimensional space. The comparison here is linear SVC is similar to the linear SVR estimator, and SVC estimator is similar to the SVR estimator classification versus the regression. Linear SVR, just like the linear SVC, does not compute the support vectors. You have to calculate them yourself. It does perhaps saves them because it does need the support vectors to be able, or I guess in the linear case, it does need the support vectors to be able to do the prediction. And then another note is that the SVR is slow to train, just like the the support vector machine classification is. With that, we are done with the SVR regression too. So I'm going to pause here. This is a small section. So see if there are any questions or experiences or perspectives to share.
Sorry, Bhanu, can you clarify a little bit the last slide? What did you mention about the no support vector attribute?
Yeah. So the linear SVC does not compute the support vectors. The implementation itself, as in the class linear SVC, similar to that linear SVR class, does not give you support vectors by default. So you do need to pull out the intercept underscore and .coef underscore and need to compute which of the training sets are support vectors yourself. However, SVR can give you the support vectors. So if you say SVR dot support vectors underscore, you will get a list of all the training instances that are tagged as support vectors.
Got it. Thank you.
Mm-hmm. Okay. Seems like anything else to share? Has anyone used SVM regression? Okay, I guess it's time to move on to the next section. Under the hood. This is a very tough section. So let's see how this goes. I tried to supplement some information, try to make it less mathy. I am not sure how I did. Let's find out. It's kind of, I'm not really sure how people like about this, but I kind of felt introducing how the support vector machine looks like in an equation form, 3 sections down into the chapter seems a little odd, but I feel like it does work for some people, especially those learners who are more hands-on and implementation based. Perhaps it works for them. But someone who has a little bit of introduction to linear regression or statistics might find this a little too late. But in any case, support vector machines are basically your hypothesis function for support vectors is just a linear combination of your features plus an intercept, pretty much a linear, just like any linear classifier. However, what this hyperplane or the decision function is what the author uses, and I am interchangeably using hyperplane, although I don't think the author uses hyperplane. Hyperplane is a term that's often used for support vector machines. So if someone did not find hyperplane mentioned in the textbook, they can replace that mentally as the decision function. So the idea is to be able to draw this 3-dimensional, in this case, 3-dimensional plane that linearly divides the triangle class here and the square class into 2 separate sections in the space. Basically, that's what it is. And h of x is that plane, and the prediction is which side of the plane you are. There is a positive side and there is a negative side, basically determined by if you evaluate how high the plane is for those points, would you get a positive number or a negative number? It's just as simple as that. So for any new data points, evaluate the h of x and just look at the sign on h of x, and then you predict a class of positive class or negative class to that. The author doesn't use positive class and negative class as in +1 and -1. He uses the labels of 0 and 1, and that's probably because it's pretty much a standard throughout the textbook, but oftentimes in support vector machine chapters in other books, people do tend to use +1 and -1 as the labels. Now, having said that, we can see that the decision boundary is what we have been seeing as the linear separable line, but in fact, what that linear separable line, is the intersection between your hyperplane and the feature space. And your margins are, we'll get to where the margins are, but let's see. So margins are where your hyperplane is +1 or -1, and there are 2 classes: positive class, green in this case, and the negative class, blue in this case. One thing I do want to mention, I hope this doesn't throw people off. A decision boundary is, or the hyperplane is scale invariant, as in if I already have a h of x, and if I multiply the h of x with alpha, your decision boundary doesn't change. What that means is I am pivoting my hyperplane above the decision function and turning it. It doesn't matter how much I turn it, my decision function itself does not change. However, my margins will be different. So during the specification, the author, Corina Cortez, I guess, Vladimir Vapnik and Corina Cortez just took advantage of that and fixed the margins such that the hyperplane is equal to +or -1, which gives you one single plane. So this is an interesting, the author introduces the training objective in a way that I have not seen before. Support vector machines, when I first learned the objective function was introduced very differently, but I really like the way the author used, the concept that author used. It's pretty clear that the hyperplane has the L2 norm is the slope because it's just a linear function, and then W is the slope here, right? And then, so the idea is that the smaller the W, the larger the margin. So that is the larger the road that you are fitting between the classes. So what your objective is to minimize W as much as you can. But that means that you can turn the hyperplane to match with the feature space until the W's becomes 0, right? But no, but you also want to avoid the margin violations. That's what makes the hyperplane not to be the weight vectors not to be 0, but some value. So this is where the author actually projects the labels from 0, 1 to +1 and -1. And so this is, I guess, another way to do it, or you can just start your labels as +1 and -1. And the objective function here is, again, W transpose W being the square of the slope. You would try to minimize that. And here is the specification that says that, which is, it's an interesting constraint, but I don't know if people might have problems understanding it, but what it simply is saying is that you want to have a plane such that your positive class stays on the positive side of the plane and the negative class stays on the negative side of the plane. And also you want to keep the training samples off the street, which means that they need to be not just greater than 0, they need to be greater than 1. What does it mean to say positive samples on the positive side of hyperplane? It means that your TI, that is the training label, and then the value of the hyperplane are either both positive or both negative. They're both positive for positive class, and they both are negative for the negative class, which means that you want all your points to be outside here. With that, let's move on to the next section. This is the soft margin training objective. This is where the hard margin was introduced by Vladimir Vapnik, and soft margin is Corina Cortez. And what Corina Cortez has done is she introduced the concept of slack variables, which is very operations research terminology. But the idea is that you do allow margin violations, but what you do is you add a value to the violation, so you still you still are faking those points that are violators as non-violators. But then just because you're letting margin violators in there, you place a cost of violating it. And so, but you also want to minimize it. So you want to minimize the number of violations, but you also, at the same time, you want to make sure that your positive classes are on the positive side and the negative classes are on the negative side. This is the quadratic programming section that author goes into. We don't really need to go into it. The idea is that quadratic programming solvers are everywhere. And so solving the SVM objective function already comes with packaged software. We don't necessarily need to build it. And it's a quadratic programming because it's quadratic in W. So with that, the next section is slightly complex. It goes into the dual problem. So this is, again, an operations research concept. It is also known as kernelization to most machine learning folks. So I'm going to just quickly show that the objective function changes its forms in such a way that you don't have any W's. That's the main thing to see here. You only have alpha i's. And what alpha i's mean, we'll kind of try to explain that in the next section, and let's see if it works. I'm going to skip this section too, but the point is to be able to construct a dual problem for the primal objective function for support vector machines, you need two things: kernelization and the kernel trick. Kernelization is basically any machine learning, especially the linear algorithms, can be kernelized. You can kernelize a linear regression, you can kernelize logistic regression, you can kernelize a KNN too. The idea is, at least under the linear regression, you have your training samples, you have your labels, and your feature space is n-dimensional here. And ultimately, you just want to learn what the parameter vector is. That's all you do as part of the linear regression. You use loss function and the gradient to be able to do the training. But what kernelization does is it tries to get rid of W's. And so you can express your linear regression not as a function of W's, but just as a function of these weights alpha I. That is what it is. That at the very high level, kernelization is nothing but getting rid of your parameters and just using weights on your training sets. So, but what that means is, I'm not really sure we should go into this, but the idea is if you do that, when you kernelize it, you have changed the way your expression looks like as a dot product between each and every training instance and the new X that you got. And so you are performing dot products against each and every instance and the new X you have, and then you have this kernel vector and a linear multiplication and summation of the kernel vector of the alphas is what your prediction would be. Anyway, so the idea is that when you, that's during the prediction time of it, but during the training, you do need to compute, to be able to compute W, you need to make a dot product between the training data and itself. And that's where the concept of kernel matrix comes along. And the size of the kernel matrix is your training instance by training instance. The advantage of kernelizing is if you take an n-dimensional feature space, project into like a really, really high dimensional feature space, perhaps even infinite feature space, you have to compute. If you are not kernelizing, you have to compute your parameters. There are infinite number of parameters. You won't be able to do that. Kernelization gets rid of that. You only have a weight per sample. And so now suddenly you're performing a linear regression in an infinite dimensional space or in a very large dimensional space. So that's the idea of the kernelization. But the problem with that is you have to memorize your data. So your model, the size of your model is the size of your data. But for kernel vectors, thankfully, it doesn't have to memorize every single training instance. It only needs to remember the support vectors. And as long as you remember the support vectors, given a new point, you would be able to do your prediction because you need to just compute the dot product between the new X versus all the support vectors. So that's the kernelization. In one sentence, kernelization is nothing but getting rid of W's. But getting rid of W's means that you are also doing this calculation of kernel matrix. And this is where the kernel tricks comes along. Kernel trick is just being able to compute dot products easily in a high dimensional space without ever even projecting into the high dimensional space. As an example, say if you have an input space of dimension n and you want to project into a really high dimensional space, capital N, by using this phi of x. The author used a polynomial function in his example, but this is the same idea. And if you want to compute the dot product in this phi of x, you need to calculate what those coordinates are for both point A and B. But what if you can do the dot product and decompose it as just a function of the dot product that you could do in the smaller input space? Then it becomes the kernel trick. That's all the kernel trick is. And the author presents various kernels, linear kernel being just a dot product between any two vectors in the input space. Polynomial kernel is dot product times a gamma plus an r raised to the power. And a Gaussian RBF is, we saw this before, and this is a universal approximator. And it also has the feature space phi of x for this is in an infinite dimensional space. And then the sigmoid using the tan H is another kernel. So with that, let's move on to the next section, which is the online SVMs and the hinge laws. We kind of briefly touched on the SGD classifier for online SVMs before in the previous sections. As you get more and more data points, you would be able to revise your parameters using the STG classifier. However, this is pretty slow, but you do need to specify loss as hinge explicitly. But this is where the author finally introduces the SVM classifier cost function, the very last section, which is same as the previous objective function the author has introduced as soft margin SVM objective function. So the idea is the hinge functions looks as shown here. What it means is, or what the geometric interpretation of this is, that for every misclassification which has a edge of 1 or negative number, you put a penalty. If you are more than 1, that means you are correctly classifying your vectors. Positive classes are on the positive side and negative classes on the negative side. So you don't have to put any penalty. That is it. And in terms of what actually the axis T represents with respect to the hyperplane and the feature space, the green arrows here points to that. So with that, I think we are done with the book, but I picked one of the most interesting comments or code that author had. If you are starting to get a headache, it's perfectly normal. It's an unfortunate side effect of the kernel trick. So with that, I'm going to again open the last section for any questions or comments.
Nicely done.
Yeah,
Thank
that was
you.
really great, Bhanu. Does anybody have any questions?
Yeah, I had a clarification question. I like the visuals you used, Bhanu, really good ones. Can you go to the slide where you talked about the alphas being 0, non-zero? Is that something that is true only for inference, like prediction?
Let me get to that. The zeta is here being 0 or non-zero?
No, it was at the dual problem. We introduced a dual problem. Yeah, the 29, I think it was 29, slide 29.
Yeah. So, right. So, so the alpha I here is the weight on a training instance that is not a support vector, which means that it's being correctly classified, which means that, as an example, here, all the blues here that are outside the margin and all the greens here that are outside the margin as alpha is 0. So we don't really need to have any weights on them. But for these, alphas are not 0. And so these are the technically or intuitively thinking, these violators are the ones that are balancing, so to speak, the hyperplane that is above them. The rest of them, it doesn't matter.
Right, they're defining the margins and the width of
yep,
the
correct. So for that reason, your alpha i's are 0 for the rest of them because they're not violating anything. They fulfill the constraint that we have placed.
Right.
But for these, the constraints are not fulfilled. So what we do is we put a weight on them until that constraint is filled, and that weight is just random. We want to minimize that penalty.
Right. So visually, that makes perfect sense to me. Computationally, are these alphas becoming 0 by the algorithm as you're trying to solve that optimization problem above?
To be honest, I'm actually not sure if the algorithm itself is trying to solve it or not, or it is being set externally. Conceptually, conceptually this is the final product. But if you take a look at the objective function itself, or the primal version of it, well, in this case, it's zeta I, but your zeta I is 0 too. It's the same concept here. If the constraint is satisfied for a given training instance, you set zeta I to be 0. And I think in this case, the algorithm sets it itself. Like it doesn't have to, you can calculate the zeta I based on, given a hyperplane, you can calculate the zeta i's. So in which case the algorithm is setting them. And I think it's a similar concept here in terms of the support vectors itself. Given a hyperplane, there are, you can define which one of your instances are support vectors and which one of them are not. So given a hyperplane, that in itself determines which of these alpha i's are going to be 0.
Got it. Thank you, Bhanu.
Hey, Bhanu. I have a little bit of intuition around this dual objective that might help. So if you look at what's on your current slide, slide 29, at the top, we're trying to minimize this large sum, okay? And people might just sort of flinch because there's a lot of letters and subscripts, superscripts or whatever. But really, what this is saying is that we have M training examples, and so I'm just going to have M weights alpha, okay? Yep. And if you look at this double sum, all it is saying is for every pair, so it's this is a square. So if we have 100 training examples, then I'm going to have a square, 100 by 100, and I'm going to compare the first one to each of the other ones. I'm actually going to compare it to itself also, and I'm going to compare the second one to all 100, and the third one to all 100, and total this will be a sum of 10,000 pairs. Okay, if you look at what it's summing in there on the left-hand side, in the big one, it's the product of the alphas, and these t functions is just going to be +1 if they're on the same side of the margin, and -1 if they're on opposite sides of the margin. Okay, and then it's a dot product between the 2 points. That's the first sum, and then the second one is just the sum of all of your alphas. So we're trying to minimize this. So that right-hand part, subtracting the alphas, you'd like your alphas to be as big as possible. That will make this thing smaller or more negative, right? And on the left-hand side, you get +1 if they're on the same side of the margin, and -1 if they're on opposite sides. So for 2 points that are on the same side of the decision boundary, you'd like alphas to be as big as possible when you're comparing them, theoretically, okay? But the problem is when you have 2 points that are on opposite sides of the margin, then you would actually like alpha to be, I'm sorry, I said that wrong. So +1, you're trying to minimize it, so you want really small alphas because you're trying to minimize this. So 0 is the best you can do. When they're on opposite sides of -1, then you would actually like alphas to be as big as possible. So if you have a little bit of intuition about that last part, there's 3 parts, the alphas, and then this +1, -1, and then the dot products. The dot product just simply, right, that's like your cosine similarity. That says how close are these points to each other. So in general, the points that are on the same side of the decision boundary are going to be closer to each other than the points that are on the opposite side of the decision boundary. So that last part is going to add more weight to all the +1s than it is going to add weight to the -1s. So the intuition that I have around this complex double sum is if you want to minimize that whole value, you basically are going to have zeros between points that are on the same side of the decision boundary for those alphas as much as possible. And then for nearby points that are on opposite sides of the decision boundary, that's when you want to crank up your alphas as big as possible, because that's going to give you the most negative value. And so ultimately what that means is only your support vectors get values of alpha. Those are the ones that are really close to each other, really close to the decision boundary. And for everything else, you just get zeros for all your alphas. I don't know if that helps, but that's the way I've tried to sort of intuit the dual problem.
And I like the way you explained the first term here, because I visualize it similar to the kernel matrix here. It's just a summation of these kernel matrix. but you just multiply each row with alpha I and each column with alpha j, and again each row with ti, and then each column with tj, and then just add them up, and that's what you end up getting this value here.
Yeah, so it's a plus or a -1 times the alphas.
Yep.
But then it's also weighted by that dot product, so that nearby points are weighted higher and far away points are weighted lower.
Yep. So your the kernel matrix itself will capture the nearness and the similarity features between the input vectors or the training instances. But the good thing is you only need to compute your kernel matrix once. And once that's done, you can just go into an exercise of setting the alphas until you minimize this. Is that correct, Ted?
I think at this point you understand this better than me. I just took some time to decompose this. At first, it looks like it's really intimidating double sum, but really it's just a square.
It is not. Yep.
It's just multiplying the alphas by each other, each I and j.
Yep.
I would like to add some intuition too. Can we please go to the hard margin case, the very first one? The formulas.
Oh, yes.
The optimization formula. I mean, how the statement of optimization.
There you go.
Here. Okay, so look at the first thing which we are supposed to minimize. If we have here variables which are marked by W. So if we have only one dimension 1, it will be what? X squared, well, W squared. It is a parabola. So minimizing a parabola is a very simple thing. But we have down here subject to, and these are actually lines. If you look at them, these are lines, and these are the sign greater than means that we have one side of the line. So it is a half plane which is bounded by a line. So these lines, they cut our parabola on pieces. And we need to minimize our value only on the accepted piece of parabola. Are you with me right now?
Yep.
Okay, very good. So we can add dimensions now. 2 dimensions. It means that we got to minimize a paraboloid. And it is subject to be cut by planes in this case, just planes. So we have half spaces here, and we have the paraboloid at which we cut, from which we cut some piece, and then we need to minimize our this formula, this square. Well, it's not exactly, it doesn't look like a square. But we need to find the minimal value of the parabola restricted to these half planes. Sorry, what I am in here, half spaces, sorry. So we can generalize it further. We will have a paraboloid which is multidimensional, and it is cut by many hyperplanes. And so we work with a rather complicated multidimensional surface on which we need to find minimal value. So I don't know if you remember, but to optimize a function on the interval, we do what? We found values on the ends of the interval, and we find derivative, and we check critical points, and we compute where all these values, and we choose minimal values. So it is very similar, which is done here, just it is a whole surface. The borders are much more complicated, And it is pretty much why support vector machines are so difficult to compute, because we get something rather complicated to work with. Okay, I can talk a little bit more about the next, about soft margin, if you want, because it is very similar. Oh, okay, here it is. So we need to minimize. Here we have a paraboloid, and we have a few new variables which do not depend on the previous at all. So it is a structure which is called paraboloid cylinder. I don't know if it is helpful, sorry for this. But you can Google it and see what it is. We just have multi-dimensional paraboloid cylinder, and the subject to it is still half spaces, hyperspaces. So sorry, because we have a restriction for hyperplanes, and the sign of inequality means that you should have only one half of the space which is restricted by these hyperplanes. I'm sorry if it was, I hope it was helpful. So I'm done. I just want to say that kernel means that our function which we minimize is much more complicated. But it is still cut by hyperplanes. And we have a piece of it where we need to minimize. Okay.
Thanks, Maya.
Thank you.
You're welcome. Any questions about it?
I had a general question. Sorry, Ted, go ahead.
Okay, so George, I'll let you go. I think this is an amazing book, and it covers such a large amount of material. So as with any chapter, we could probably go on for a long time and go very deep. But George, I'll let you have the last question or comment, and then we'll wrap things up for this week.
Thank you. Yeah, I appreciate it. So I like the computational complexity that the author did for classification. I did not see anything similar for regression, and I'm trying to think if it's similar or if it's more computationally intensive than classification. That was just mine.
Regression has n² complexity, actually. So it is better than kernel trick when you use a kernel, but it's not as good as when you work with linear case. If you mean just regular regression, because elastic regression, it is more computationally intense.
Yeah, regular regression. I would imagine it would depend both on the features and the number of training instances, right? I think it would be similar.
No, I think George is asking if you do, instead of a linear support vector classifier, if you do a linear support vector regressor, is it the same time complexity?
Right.
I don't know the answer. I think it is. I don't know if you know, Bhanu.
I don't either, but I do think it's the same because of the way the objective function and the constraints are written down.
Okay, something to think about. Thank you. Thank you both.
All right. Awesome job, Bhanu. I really loved this presentation. Thank you so much for leading the discussion this week. So
thanks for the opportunity.
Yeah, this is awesome. So we're gonna wrap things up here with this chapter. Next week, we're going to be doing chapter 6, the decision trees chapter, and we'll keep going through the book. So for those of you who are not continuing on for the project discussion, you're free to drop here, and we hope to see you next week. Otherwise, for those of you who joined, thanks for waiting. We tend to go over, there's just so much material. We tend to go over every week, just as a warning, but we appreciate you coming and joining us. And so now we're gonna shift gears, and this is the hour when we take questions. People have programming questions about formulating machine learning problems, and people can also just kind of talk about projects that they're working on and things like that.